Okay, good evening. So, this is our lecture number 34, and in the previous lecture, we started our discussion on the computational methods on multi-phase flow. Okay, so if you recall, I have given you some idea about the different approaches of computations which we can utilize for multi-phase flow problems. Okay, and as I told you previously, also that majorly in this course, we will focus on the direct numerical simulations of multi-phase flow. Okay, so whenever we will be doing the direct numerical simulations, our aim is to characterize the interface at each and every locations and at each and every time interval. So it means I want to analyze the spatio-temporal evolution of the interface. Okay, so that is something which we want to do. So if we have to do the spatio-temporal evolution of the interface, we need to basically specify the formulation of the interface. Okay, so our numerical solver or our mathematical model should include the initial definition of the interface. It means it should specify the positions where interface is located. Okay, and once the initial location of the interface is specified mathematically, then it should be also able to move that interface with the flow, because interface will be moving with the flow depending upon the flow dynamics and physical phenomenon which is happening. So that's why our mathematical equation should be capable of two things. First, these should be capable of initially describing the shape of the interface and then evolving the shape of the interface because of the different physical phenomena which are happening. Okay, so particularly say if your physical phenomena is flow through a two-phase flow through a pipe, then it will be interface will be evolving because of the say pressure difference across this or some velocity difference across the interface. Okay, and if say physical phenomena is also involved with some chemical reactions which are taking place, then there will be mass transfer because of the chemical reaction, and because of that also interface can evolve. Okay, and if say physical phenomenon is involving the phase change heat transfer, then there can be the process of boiling and condensation. So movement of interface will be because of the surrounding flow as well as because of the phase change. Okay, phase change will also say if you have one vapor bubble, okay, and in its surrounding there is liquid. So if this liquid is getting converted into vapor, then what will be happening? This will becoming a larger portion of vapor. So because of this phase change also interface can evolve. Okay, so these are the different things. Obviously all the phenomenon at the same time we cannot consider, means for the initial understanding. Of course, mathematically or computationally we can handle a situation which is having multiple phenomena responsible for motion of the interface, but whenever I will be starting this description, I will be taking each and every phenomenon one by one. Okay, so first let's talk about interface description. Now interface can be described in multiple ways. So one of the first type of function is called as height function, which can be utilized to describe an interface. So let's consider that I have a two-dimensional space x and y. In this two-dimensional space, this red curve is nothing but my location of the interface. So it means above this, say I have phase 1 and below this I have phase 2. Okay, now what I can do, say this I have taken some reference, and with this reference if I measure the height of the interface h, then I can define that if this photograph of the red colored line is taken at some time t, then I can say that h of x comma t is my height function for this particular location. Okay, so likewise if I define the height for each and every location, then I can write that my y coordinate is nothing but equal to h of x, because value of h is different at each and every location. So this type of description of the interface at different values of x, what is the value of h of x? That will be giving you the location of the interface. Okay, so this is called as height function based description of the interface. But this type of interface description has some challenges. What are the challenges? Here you can see that up to this point it is working fine because it is giving you the unique value of the height function for every value of x. Okay, but if you go after this point, then what will be happening? Here, how many values you are having? 1, 2 and 3. Okay, so when interfaces are complex, okay, during that time what can happen, that height function at a particular value of x may have more than one value. So under this scenario, it will be becoming extremely challenging for you to characterize and define where is your actual location of the interface. Okay, if you have multiple heights, then of course whenever you have seen this physically for the first time, then you can simply say that okay, it will be of 3 heights in this order, it will be of this shape. Okay, but once you have not physically seen, your simply mathematical function is giving you some numbers. Once you have to simply deal with the numbers, at that time it will be becoming challenging for you to determine the exact location of the interface. So height function based method is very good in terms of defining the interface for majority of the situations, but if you have very chaotic and multi-layered interfaces in these scenarios, this method can become very complex. Okay. Then, but there are certain ways to use this method. And if you have to use this method for 3-phase system, then for 3-phase system, how you can use it? For 3-phase system now, instead of a line, what you will be having? You will be having a surface. Okay. If you have to define the height of the surface, you will be requiring how many coordinates? 2 coordinates to define that, and third one will be defining the height. Okay, so say if I do take situation like this, this is my x direction, this is my y direction, and say this is z direction. Now say I have a plane something like this. Okay, so if you have to define the height of this plane in z direction, then how you can define? To locate any particular point on this plane, you have to specify the corresponding x and y coordinate, and for each and x and y coordinate you will be having some specific height. Okay, so this is how, by knowing the height, actually you can define the interface. So first method is height function based method. Now let's talk about the second method. Second method is actually parameterization. Okay, so in terms of parameterization, we will be defining some coordinate, or we will be defining some parameter which is able to define us the values of x and y corresponding to only interface. Is this point clear? So what I have done, I assumed that if this is my fluid 1, this is fluid 2, so then this black colored line is nothing but interface. Over this interface, this particular direction is of parameter u. So it means parameter u is perfectly aligned with the shape of the interface. Is this point clear? Now, if I measure the values of x and y only along parameter u, what I will be getting? I will be getting nothing but the position vector of the interface. Is this point clear? So that is what I am saying over here. Position vector of interface considering argument u. Argument u means I am always pointing on this. Okay. Corresponding to this, I will be getting different values of x and y. So this type of approach is called as actually parameterization approach, where we have defined some mathematical parameter which is exactly matching with the shape of the interface, and using that parameter as argument for the position vector, we can now define the locations or position vector of the interface. Is this point clear? So that is what I have written over here. Now when you define interface mathematically, then the interface definition itself does not serve the purpose, because ultimately what you need to do, you also need to, along with defining the initial location of the interface, you also need to evolve this interface with space and time. So if you have to evolve the interface, you have to define that what are the velocities at the interface in tangential direction to the interface, what are the velocities in normal direction to the interface, because the velocities which are normal to the interface, these will be responsible for its motion within the flow domain, either its extension or say receding, contraction. Okay. So what we need to do, we need to define these. Moreover, if you recall from our earlier knowledge, we have also seen that at the interface some forces also acts. Okay, so at the interface we define two types of boundary conditions. One is kinematic boundary conditions and second is dynamic boundary conditions. In terms of kinematic boundary conditions, we only define the interface velocities parallel and normal to the interface in different sides of the interface, and in case of dynamic boundary condition we do balance of forces across the interface. Okay, so to define all these forces and the velocities at the interface, which will be helping us in evolution of interface with space and time, we also need to define the directions, tangential direction and normal direction to the interface, and third important parameter which we need to define is curvature of the interface, because there are some of the forces which acts on the interface and these forces are proportional to the mean principal curvature of the interface. What are the forces which are responsible, which are defined using the mean principal curvature? Please tell me. We have already studied this while we discussed the shapes of the bubble, bubble dynamics, drop dynamics. Surface tension force. What is surface tension force? Or pressure change because of surface tension. Delta P for a bubble, say delta P is equal to 2 sigma by R. So what is 2 by R? It is nothing but mean principal curvature for a spherical bubble, and sigma times mean principal curvature is nothing but our surface tension force, which is causing the difference of pressure on two sides of the bubble. Okay, so that is what I am trying to say over here, that curvature is important because whenever we will be defining the forces, then curvature will be taking important role in defining these forces. Okay, so in addition to the mathematical description of the interface, its tangent, its normal and its curvature are three important parameters which we should be able to define mathematically. Okay, so now how to define tangent? If I consider this position vector dx of the interface and if I take its derivative with my parameter u, then dx by du will be giving me some vector which is nothing but tangent to the interface. Is this one clear? And then third important point is, if I consider that, now till now what I have done, I have defined this u to be some parameter which is actually defining the interface. But how u can be parameterized? Okay, so for that one simple formulation can be, if I assume that at any point whatever is my curvature, with that curvature if I have say ds as my small arc length of this surface, then ds square can be written as dx square plus dy square. Okay, so in that sense, for that small part of the interface ds, I can write tangent vector to be dx by ds. Is this one clear? So nothing but u, I am substituting the mathematical formulation of the u for a small element, and u I am writing as ds, which can be written as dx square plus dy square. Okay, now one important point, because this is nothing but a unit tangent vector, what I am doing now, I am writing these direct formulations. If you have to see the entire derivation, that how dx by ds or dx by du becomes a unit tangent vector, you can refer your book, this direct numerical simulations of multi-phase flow. Okay, so in that particular book, if you refer to the appendix section, there they have given the full mathematical derivation how unit tangent vector can be written as dx by ds. So that derivation I am not doing at the moment. Okay, so just I am giving you the final results because that is something which is more useful to us, and if we are doing numerical simulations, then this is what is being calculated in the numerical solver at the back end. So let me explain you that part only, but if you want to go for detailed derivation, you can refer the appendix of the book Direct Numerical Simulations for Multiphase Flow. Okay, so unit tangent vector is dx by ds. If this is unit tangent vector, then of course its magnitude will be equal to 1. Okay, this point is clear. Now, if this is my tangent vector and this is the unit normal vector, then ultimately what will be happening? These vector has to be at 90 degree to each other. Tangent and normal will be orthogonal. As these are orthogonal, so their dot product has to be equal to 0. So t dot n will be equal to 0. It simply means that if my t vector has two components t1 and t2, then dot vector will be satisfied only if my normal vector has components t2 comma minus t1. Okay, so if I know the components for a two-dimensional curve, if I know the components of the tangent vector, then I can simply know the vectors of the components of the normal vector by doing this computation. Okay. Now, one important point is, if I take the derivative of unit tangent vector with surface, okay, then that is nothing but proportional to the normal vector. Again, derivation I am not doing here, I am simply directly giving you the formula. So you have to understand this point, that derivative of the unit tangent vector with the surface is nothing but proportional to normal vector, and this proportionality can be converted into equality with the help of kappa, where kappa is nothing but mean principal curvature. And similarly, if I do the derivative of normal vector with s, that comes out to be minus kappa into tangent vector. Okay, so these are called as Frenet-Serret formula. Okay, so standard mathematical results, that derivative of tangent with the surface is equal to mean principal curvature times normal vector, and derivative of normal vector with the surface is minus mean principal curvature times tangent vector. Okay, so these are nothing but standard results. Once you have defined the tangent and the normal vector, these two formulas can be utilized to determine the value of the mean principal curvature. Okay, how? If you take dot product of this entire equation with normal vector, what will be happening? On the right hand side, n dot n will be equal to 1. Okay, because n dot n will be magnitude of this is unit normal vector, so magnitude will be 1 and cos of 0, so it will be unity. This will be unity, so I can write by doing this that curvature is nothing but equal to n dot dt by ds. Okay, similarly in the second equation, if I do t dot on both sides, then it will be minus t dot into dn by ds. Is this one clear? Okay, so it means if I know the normal vector at any surface, or if I know the tangent vector at any surface, then by utilizing these two, I can define the mean principal curvature. Is this one clear? Now, when we define the curvature and when we define the normal, then it is important to define the directions for both curvature as well as for the normal. Like with their magnitude, there will be some sign also. Okay, so typically always our assumption is, if we have some curve, any vector which is pointing outward from the curve, that we say as unit normal vector. So that is the standard notation. Okay, so if my unit normal vector is pointing in a direction and curve is folding in the other direction, then my curvature will be less than 0. But if the unit normal vector and fold of the interface are in the same direction, then typically curvature is considered greater than 0. Okay. So using unit normal vector always away from the interface may give difficulty while we solve the multi-phase flow problems, because this may not give the equal basis for defining the normal vector for different phases, because sometimes it may happen that your shape of the interface may be something like this, sometimes shape may be like this. So at different locations, if fluid 1 and fluid 2 are interchanging, swapping with each other, then what will be happening? Then your definition of the normal will be actually becoming confusing. Okay. So typically whenever we do the computations of multi-phase flow, what we do? We define fluid 1 on one side of the interface, there will be fluid 1, and on other side of the interface we will be having fluid 2. So typically when we do the computations, we define one reference phase. We define one reference phase, and usually fluid 1 is considered our reference phase. Okay. So whenever we will be doing the computations, we will be defining one reference phase, and typically our fluid 1 is nothing but the reference phase. So it means that whenever I will be defining the normal, always I will be pointing it away from the reference phase. That is the nomenclature which I will be using. Okay. So here I can say that if normal is pointing away from the reference phase, it means this is my fluid 1 and this is fluid 2. Is this one clear? So using this we can actually fix the direction of the normal. So normal will be always pointing away from the reference phase, which is nothing but fluid 1 for our case. And if in the direction of the normal we are seeing that interface is folding, then curvature will be positive, otherwise it will be negative. Okay. Now this is working fine for a two-dimensional space. What will happen for a three-dimensional space? Okay. So for a three-dimensional space, you will be having a complete, in case of two dimension, your interface was nothing but a line. Okay. But in case of three dimensions, interface will be a surface. So when interface is a surface, then instead of using one parameter for parameterizing the interface, you have to use how many coordinates? 2 coordinates for defining the interface. Okay. So that is what it is done over here. So here you can see one is this direction. So these are nothing but constant u lines. So likewise you can have another line. So these will be the constant u lines, and this is constant v lines. Okay. So these constant u lines and constant v lines which are wrapped around the interface, these will be forming a net spectrum along which you can define the position vector of the interface. So position vector of the interface will be nothing but x at u comma v, y at u comma v, and z at u comma v. Okay. When we have a three-dimensional space, we will be requiring how many parameters? 3 parameters to quantify the interface. Okay. We will be requiring 3 coordinates. But how many parameters? Only 2 parameters, because interface is nothing but a surface. Okay. And we are, if defining our parameter such that it is wrapping along the surface. So what it means? That my parameters required are only 2, but coordinates required to define the interface will be nothing but 3. Okay. Is this one clear? So here this is small elemental area d delta A. On this elemental area now, if you see, there will be actually multiple vectors. Okay. So one is this x u XU is nothing but tangent at this location. This is a tangent vector, but this is tangent along the U line, constant U line. Okay, and this XV is another tangent vector, but this tangent is along the constant V line. Is this point clear? All are clear with this idea? If you recall from the two-dimensional space, what we have done? In two-dimensional space, if I simply use dx by du, that was becoming tangent along that path u. Okay, that was becoming tangent along path u. Now, if I do del x by del u, what will be del x by del u again? It will be tangent along line u. Is this point clear? So, xu is nothing but tangent along line u, and dx by del x by del v is nothing but tangent along line v. Point is clear? This is very simple. So, if you have, say, a curve in between u and x, this is the curve. So, if you have to define slope at this point, how you will be defining the slope? Del x by del u, and this is nothing but tangent to this point. Okay, so that is what I am saying, that del x by del u will be tangent in the direction of constant u line, and del x by del v will be tangent in the direction of constant v line. So if I know these two tangent vectors, both of these will be nothing but in the same plane but perpendicular to each other. Is this one clear? So both of these two tangents are on the same plane but perpendicular to each other. So it means that if I take their cross product, so I will be getting some vector which is normal to this plane. Okay, normal to the surface at that point. So that is what I have done. Now I can define my normal vector as nothing but product of xu cross product of xu and xv, and divided by their magnitude, because I want to define the unit normal vector. All are clear with this idea? Okay, and I also know from my previous discussion that if I have to define curvature, that curvature is nothing but n dot into dt by ds or t dot into dn by ds. So in the similar way, if I take the surface gradient of the normal vector, unit normal vector, that will be nothing but giving me the value of the curvature. All are clear with this point? So what I have to do, I have to consider, if you see previously what we have, dn by ds. dn by ds, we have the gradient, and that gradient is dot product with the tangent vector. So it means this is nothing but surface gradient. So mathematically, the full definition is along the tangent to the surface if we are taking derivative of normal. Okay, so that's why I am writing it as nothing but minus surface gradient of surface divergence of the normal vector. Okay, but again what you can do, you can go to that book and you will be finding that this can be written even in terms of normal divergence operator, del dot n. Okay, so curvature of any surface can be defined in terms of minus divergence of n if you have nothing but a three-dimensional space. Is this one clear? So this is one method of defining the curvature. Now curvature can also be defined using second method. So using the second method, how it can be defined, let me consider that this is nothing but my edge of the, this is simply nothing but my edge of this surface. So you will be having a complete three-dimensional surface. So if I simply take any one edge on the surface, so it means if I take any one line on the surface, so on that particular line, if I take one tangent vector to the line and one normal vector to the line. And this normal vector to the line I am calling it as P, but this is normal to the line, but it is lying on a plane which is tangent to the surface. Are you clear with this point? What I am saying? I have taken an edge. To that particular edge I am considering one perpendicular vector. So that is normal vector. But this normal to this edge can be oriented in any direction. It can be in this plane, it can be in this plane, it can be in this plane. Because in any orientation you take it with reference to the curve, with reference to this edge of my hand, it is always making an angle of, say, it is always making an angle of 90 degrees. If I take it at this angle, at this angle, at this angle, every time it is making an angle of 90 degrees. But if I consider that this is the edge and to this edge, this is my tangential plane. Okay. So in this tangential plane, if I have to define normal vector, then this hand I have to keep always like this. Okay. Such that it is tangential to this surface. All are clear with this point? So it means normal, if I have to only define normal, I can have any orientation of my this hand. But what I am saying that I am defining normal in such a way so that it is defined on tangent plane of this. So if I define on tangent plane, then it has to be like this only. Okay. So that is what I am calling P. So P is nothing but a vector which is normal to the edge, but it is tangential to the plane. Okay. So now if you know this, then what you can do, you can simply do the line integral of this normal vector over the closed contour, considering that your elemental area is very small and it will be giving you the product of curvature and the normal vector. So this is third definition of third method for defining the curvature. And how you can obtain this vector P? So if you know the n vector, normal vector to the interface, and on the particular edge along which you are taking this P vector, if you simply define tangent along that, then the product of the normal vector, because normal at this edge will be pointing in this direction, so product of this normal and this tangent will be giving you nothing but P vector. Okay. So this is another method for defining the interface, then its normal, tangent and curvature in three-dimensional space. Okay. Now let's consider next method. Next method for defining the interface is based on a step function. Okay. So the meaning is, this is a two-dimensional plane x and y. Okay. And in this two-dimensional plane, say this grey colored portion is my fluid 1, and say this white colored portion is my fluid 2. Now I will be defining some function. This is nothing but identical to your phase density function, phase distribution function. What was phase distribution function in our experimental methods? Phase distribution function was that its value will be 1. It will be giving some output when I am in phase 1, and if I am in phase 2, its output will be 0. Okay. So like phase distribution function, this is nothing but step function I am calling it over here. Okay. So I am defining h of x is equal to 1 if it is inside a closed interface, and if outside the closed interface, then it is equal to 0. So this is the closed contour over here, and in this closed contour you can see that outside everywhere h is 0, and in this closed contour I have shown this slightly above than the surface to indicate that h is equal to 1. All are clear with this point? Now if I have any element, small element inside the curve whose volume is dv dash, such that its coordinates are dx dash and dy dash. Because in third direction we are not taking anything, so third direction is nothing but unity. So its volume will be dx dash into dy dash, and the total volume of this entire contour is actually V. Up to this point, is it clear? Now, and of course, the surface which is indicated by this entire contour is S, and ds dot is the surface of this small elemental volume. Okay, so if I have to define the value of h, step function h, as function of x and y, I can take the volume integral and then I can use this one-dimensional delta function over here. This is nothing but my one-dimensional delta function. So this one-dimensional delta function I will be using as x minus x dash and y minus y dash, and then I will be doing this integration over the dv dash for entire volume. Okay, so small elemental volumes, if I take likewise, and then for each element I see that what is the value of this delta x minus x dash. It means that if x is pointing equal to x dash, then this delta function will be equal to unity. If I am pointing to any point other than the outside the x dash, then its value will be, the value of one-dimensional delta function will be equal to 0. Okay, so product of one-dimensional delta functions, if I do and then if I do this integration, it will be finally giving me the entire discontinuous h function. Okay, step function, and the gradient of this function will be nothing but equal to delta s into n. Okay, so where delta s is again nothing but the one-dimensional delta function, one-dimensional delta function to define interface. What is the meaning of this? When I am writing delta s, it means at the value of delta s only it will be equal to 1 when I am calculating it on the surface. But if I calculate it at any point other than the surface, then its value will be equal to 0. Okay, and why gradient of h will be equal to normal? Because you can see that if you calculate the gradient of this h within the entire entire contour, here it will be equal to 0 because you have the constant value, and if you calculate here also it will be equal to 0 because here also you have constant value. So where gradient of this is existing? Gradient of this is existing only at the interface. Okay, and if you calculate gradient of a contour, what it does? Gradient of a contour always points the direction normal to the uniform value of that function. Is it clear or not clear? Have you studied your basic fluid mechanics? So in the basic fluid mechanics, what we do, we say that if this is my pool, okay, this is the pool which is having say water over here and gravity is acting in this direction, and say this is my air. Then what happens if say PA is the atmospheric pressure at this point? If I have to calculate pressure at any arbitrary location P, that will be equal to PA plus rho GH. Okay, and if I draw the lines of constant pressure, how these lines of constant pressure are? These are the lines of constant pressure. Okay, now if here I have to calculate the amount of force which is acting on any control volume within the fluid, you will be finding that on this control volume, from left side and right side, the magnitude of the forces will be same. So these force will vanish, but only force will be available in the vertical direction. And what will be the magnitude of the force in the vertical direction? del p by del z, if say this is my direction z, del p by del z is equal to minus rho g. That is something we do. Okay. So what I am saying, I am calculating gradient of P, pressure, and gradient of pressure is pointing in which direction? That is becoming equal to gravity force. So it means it is pointing in normal direction. Okay. And if you see, this normal direction is nothing but perpendicular to the uniform value of pressure. Is this point clear? So if you have gradient of any quantity will be always pointed in a direction normal to the uniform value of that particular quantity. Okay. Simple meaning is, say if I have different values of this, again you can talk about heat transfer. In heat transfer, if my temperature is indicated by, say, constant circles, these concentric circles are nothing but showing the different values of temperature. Say this is some T1 temperature, this is T2 temperature, this is T3 temperature. If you calculate gradient of temperature, ultimately if you have to calculate rate of heat transfer, what it will be? Minus K into gradient of temperature. Okay. So gradient of temperature, and we always say that isothermal lines and heat transfer lines are normal to each other. So it means if you calculate gradient of temperature, that will be pointing a direction which is normal to the, everywhere it will be normal. So it means gradient of temperature will point a direction which is always normal to the uniform value of the temperature. Is this point clear? So fundamentally, wherever you calculate gradient operator mathematically, always it will be telling you that gradient of any field variable will be always indicating the direction which is normal to the uniform value of that particular function. Okay. So that is what I am showing over here, that if gradient of this discontinuous step function, it will be only coming non-zero at this point, and at all other points it will be 0. So if it is coming non-zero at the interface, gradient of this function will be nothing but pointing the direction which is normal to the interface. Is it clear? So that's why I am writing it equal to normal vector, and this normal vector is defined at the interface. That's why it is defined with delta S. Okay. All are clear with this point? Now fourth approach. So this was the third approach to use discontinuous function. Fourth approach is, we will be defining the interface, but despite using a discontinuous function, we are using a smooth function. Okay. Say I have this thick black colored line is nothing but my interface, and along the interface I have multiple lines which are just adjacent to the interface. Okay. And at different lines I have different values. Say corresponding to interface, my value of f is equal to 0. Other than interface, say this value is -1, -2, -3, -4, something like this. Different values I am having. Okay. And in one side I am having positive values, say 1, 2, 3, 4, 5. Like this I can have thousands of infinite number of contours. Now I have specified that corresponding to the interface, value of this function is 0. Now this is not a this is not a discontinuous function, but it is a smooth continuous function. It means earlier what was happening, either when there is fluid 1 you have value 1, when you have fluid 2 you have value 0. But in this case, even within the fluid 1 also you may have different values of function, and in fluid 2 also you may have different values of function. So this is nothing but a smooth function, and corresponding to the interface you assumed that the value of function is equal to 0. Is this point clear? So this is nothing but smooth variation along the function. Now, what we are doing, we are considering that if this is equal to 0, then you can calculate the gradient of function at each and every point now, because this is a smooth continuous function. So value of gradient will be known at each and every point. But if I calculate the value of gradient of this function at this particular location corresponding to its value f equal to 0, okay, so again it will be pointing a direction normal to the interface, but it is not a unit function now. So if it is not a unit function, so its gradient solely will not be equal to normal vector, but it will be some vector in the direction normal to the interface. So to make it unit vector, what we have done, we have taken the gradient of this divided by magnitude of gradient function of this f. Is this one clear? So this is one important smooth continuous function which is called as level set function. Okay, so later on I will be introducing you to the different methods for evolution of the interface. One of the method is actually level set method. So this smooth function forms the basis for the level set method. Okay, so typically normal over here will be minus gradient of f upon gradient of f magnitude, and curvature I have already defined you in the previous slides, that curvature can be simply written as minus of gradient of the, minus of divergence of the normal, unit normal vector. So divergence of gradient f by gradient f magnitude. Okay. Now along with this, if you want to utilize this function, what is the utility of using this smooth function? The utility of this using this smooth function is that if you can propagate the value of this smooth function with the fluid flow, okay, if you can advect the value of this smooth function with the fluid flow, then you can define the new location of the interface also. So that is what is being done over here. Say my velocity of the interface is given by u, v, comma t, where u, v are nothing but parameters corresponding to the interface location and t is time instant at a given time. So that can be written in terms of del by del t of position vector. If I know the interface position, if I do del by del t of that, then I will be getting the total interface velocity. But this interface velocity, if I have to calculate in normal direction, then what I will be doing? I will be taking the component of this velocity in the direction of normal. So that is, I will be multiplying it with the unit normal vector. Okay. So if I do n dot of del by del t of position vector of the interface, that will be giving me nothing but the normal interface velocity. Is this one clear? This will be giving me normal interface velocity. Okay. All are clear with this point? See, at interface your velocity vector can be in any direction. Say if this is the velocity vector, then it will be having two components. One component is in this direction, which is Vn, and one component can be in tangential direction, which can be Vt. So what I am saying over here is actually Vn. Okay, we are calculating normal component. Why I am calculating normal component of velocity? Because tangential component of the velocity will be responsible for interfacial shear, and normal component of the velocity will be responsible for movement of interface, either its extension or its contraction. Point is clear? Only the normal component of the velocity will be responsible for movement of the interface in inward or outward direction. Tangential component over the interface will be only responsible for the interfacial forces. Okay, so it means that if you have to move the interface with space and time, you should know the normal component of the velocity. All are clear with this point? Now one simple question to you. If say I consider that this is the interface location and everything inside and outside is stagnant. There is no motion within this fluid 1, no motion outside interface in fluid. In that case, what will be happening? Interface will always remain at its location. Okay. But if I say I have some interface velocity in outward direction, then what will be happening? This interface will be shifting in this side. If I say that interface velocity is in bottom direction, then it will be moving in this bottom side. So it means that interface will be only advecting with the flow. It is not having any type of diffusion. All are clear with this idea? So typically, if we talk about heat, say if I say heat is concentrated in this zone, then heat is nothing but indication of differences in temperature between the different location. So you cannot keep heat confined at any location. What will be happening? Because of the molecular diffusion, heat will be diffusing from one location to other location. Similar is the issue with the concentration. If you can keep one gas contained in one thing, if say there is gradient of concentration, then from one end to other end it will be actually diffusing. But if you consider that you have two immiscible fluids and everything inside and outside is stationary, then you will be finding that your interface location will not actually change. Interface will remain at that particular location only. So it means that if you have two immiscible fluids, okay, which are non-reacting, there is no reaction, no concentration gradient, okay, at the moment you also consider no temperature gradient, then you will not be finding any, and no velocity, no pressure gradient, then you will not be finding any change in interface location. So it means that interface between the immiscible phases will not diffuse, okay, but if there is some velocity, then because of the velocity it will be moving its location. So it means interface between two immiscible fluids will be having purely advection. Is this one clear? So interface will be purely having advection. So that's why what I can do, this function whatever I have defined, this is superimposed with the interface. So if interface move, then ideally the value of this function should also change. It should also translate with the motion of the or advection of the fluid. So that's why what I am writing, del f by del t over here represents the rate of change of value of this function f with time. Is this one clear? Del f by del t is nothing but rate of change of level set function with time, and u dot gradient of f represents its advection because of the fluid flow. Okay, it is nothing but advection because of the fluid flow. So its rate of change with time will be plus advection will be nothing but equal to 0. Unless or until you have any reaction involved, reacting species involved, or you have any phase change heat transfer involved. Because other situation can be that inside this, if you have some heater which is leading to boiling, so because of the boiling, even if your flow velocity at the interface is 0, then also because of the boiling some new mass will be added and there will be movement of the interface. Okay, if there is condensation, then mass will be changing from vapor to liquid, there can be contraction if I consider this to be a vapor phase. Okay, so along other than the advection, phenomenon of reaction or any chemical reaction or phase change can also lead to movement of interface. So provided that there is no phase change or no reaction involved, the movement of the interface will be purely because of the advection of the fluid. So that's why I can write del f by del t plus u dot gradient of f equal to 0. Is this point clear? This is nothing but advection term, this is temporal term. Okay, and in general this can be written as total derivative. Now from this definition that normal vector is equal to gradient of f by gradient f magnitude, I can write gradient of f as nothing but minus n into gradient f magnitude. So that is what I have done. This gradient f I have replaced with n into gradient f. Now u dot n, what it will be becoming? U dot n will be becoming velocity value in the normal direction, normal to interface. So normal to interface velocity, when it is multiplied with gradient of f, magnitude of gradient of, that is equal to 0. So this is the equation which can tell you how your value of this smooth function will be changing with space and time because of the flow. So if you are able to predict the value of change of this function with space and time along with the flow, you can actually identify the new location after any time t for your interface. Is this one clear? So my meaning, what I want to say is, say when this value will be changing, so it may happen that now at some new location, this line is occupying value 2, this line is occupying value 1, and this particular line is occupying value 0. Then this particular line will be becoming the new location of the interface. And while it is changing from this point to this point, it is not always necessary that all the lines are moving parallel distance in the same amount of time. Depending upon the magnitude of the normal velocities at different locations, their movement can be different. So that's why the evolution of this function can lead to even change in shape of the fluid entity. Is this one clear? So this is very elementary thing. Of course, we are understanding now from the theoretical point of view only. When we have to implement this in the mathematical form for doing computations, then it is actually more challenging. And how to do that, interface advection schemes, that I will discuss in the later lectures. But here just I want to give you idea. So have you understood this point? Now comes important point. When we are at the interface, little bit idea I have already given you. Again quickly I will just go through this, because while we were talking about the kinematic and dynamic boundary conditions, then also I have given you some idea. Okay, but what is the relation over here, that I want to actually just emphasize to you. I told you in the previous discussion that we can model multi-phase flows using two different approaches. The two approaches are, one is two fluid approach and second is one fluid formulation. Okay, so in case of two fluid approach, what we will be doing, first phase I will be solving separate continuity, momentum and energy equation. Second phase I will be solving separate continuity, momentum and energy equation. When I am solving the separate equations for each phase, but I will be encountering some zone where there is interface. So at that particular interface, I need to supply nothing but the kinematic and dynamic boundary conditions. Okay, so that I will quickly recapitulate over here. And second approach is one fluid formulation, where for your entire domain you are only solving your combined continuity, momentum and energy equations, combined phase equations. You are not considering separate each phase. Okay, so because two fluid approach I have already also discussed, let me quickly recapitulate how mathematically different boundary conditions can be imposed at the interface. Okay, so if you consider that this is your interface and this dashed line is nothing but a control volume which is marked at the interface, and let's consider delta V is its volume, delta S is its surface area, U1 is velocity on one side of the interface, U2 is velocity on other side of the interface, N is unit normal vector from the interface, and V is velocity of the interface. This is nothing but velocity of interface. Okay, so if you have to write over here mass conservation, considering that the thickness of this interfacial control volume is extremely small. Okay, thickness of interfacial control volume is extremely small. The meaning is, what is the meaning of this? If thickness of interfacial control volume is small, what is the meaning of this? Control volume will not store any mass. Okay, so whatever mass it will be having inflow from the left hand side, that has to be equal to mass flow outflow of this control volume. Okay, so from the inflow you can see if u1 is velocity vector of phase 1, okay, at interfacial boundary just below the interface. Is this point clear? Just below the interface your fluid velocity is u1. If you multiply this u1 with normal vector, if you take dot product of this, it will be giving you nothing but fluid velocity of fluid 1, fluid velocity of phase 1 in the direction normal to the interface. Okay, and if interface is also moving with some velocity v, then the rate at which mass of fluid 1 is entering into the interfacial control volume will be nothing but u dot n, u1 dot n minus v, relative velocity times rho 1. This will be the mass flow rate per unit area of the interfacial control volume. Is this point clear? Now, what will be a mass outflow? Mass outflow will be rho 2 into u2 dot n is the velocity of fluid 2 in the normal direction minus v and rho 2. And why these inflow and outflow masses are same? Inflow and outflow masses are same because my control volume thickness is infinitely small. Okay, very small thickness. Okay, so that's why I can say that at the interface in velocity will be equal to out velocity. In inlet mass flux will be outlet mass flux, which is equal to m dot. Okay, now this mass flux across the interface will only come either if I have reaction or I have phase change. Then only along relative to the interface I will be having mass inlet and mass outlet. Is this point clear? Relative to the interface, mass inlet and mass outlet will only be there if I have phenomenon such as chemical reactions or phase change. If there is no chemical reaction or no phase change, corresponding to that, mass flow rate relative to the interface motion will be equal to 0. In that case, what will be happening? Say whatever mass I am having in fluid 1, only that is propagating with the flow field or with the time. Okay, it is not changing. So because of that, when m dot is equal to 0, corresponding to that you will be finding that normal velocity to the interface will be nothing but equal to normal component of velocity in fluid 1 and normal component of velocity in fluid 2. So that is the reason, if you recall earlier also I told you that if there is no phase change, and if say this is like this is your interface, say below this is water and above this air. So if there is some oscillation in the water, then what will be happening? The rate at which this interface is moving in vertical above direction, whatever is the velocity just below the interface in the water, same will be velocity just above the interface in the air, in the normal direction. Right now I am talking about velocity in the normal direction. But this normal velocity will be only equal when my mass flow rate is 0. It means there is no evaporation, there is no condensation, there is no boiling, there is no reaction. Point is clear? So this is the more generic formulation. Okay. Then second point is concept of tangential velocity. Okay. So what about tangential velocity? If we have a solid wall, what we say? At a solid wall, velocity is equal to 0. Velocity just adhere to the velocity of the solid wall. Likewise, whenever we are defining the interface between the two immiscible fluids, we assume that our interface is nothing but sharp interface at the macroscopic or mesoscopic level. Of course, if you look into the microscopic level, if you look into the scale of few nanometers, then you may find that near the interface there will be some portion, as I told you earlier also, where molecules of both the phases are present. So that is interface. But if you look at macroscopic or microscopic level, that nanometer thickness of the interface is just negligible. Okay, so interface is appearing nothing but a sharp boundary to us. So if it is appearing as a sharp macroscopic boundary, so in the tangential direction, no slip condition should satisfy. So it means that whatever will be the velocity at the fluid 1 in tangential direction, same will be velocity in fluid 2 in the tangential direction. So that is what we say, that u1 is equal to u2, or for any property in general we can say that us is equal to 0, where say x is any property, x of s represents nothing but x2 minus x1 is equal to 0. Point is clear? So it means at the interface, considering that interface is sharp, we will be having existence of the no slip condition, which will be clearly defining that at the interface we have high amount of shear stress, okay, which is allowing the molecule just to have same velocities. Okay. Now, in certain cases, if say we have boiling, condensation, etc., or when we are looking into the interfaces in the molecular level, then we may have some partial slip between the two velocity values. Okay, so how to account for these partial values, that is something is defined for a solid wall over here. So you can consider, say this is a solid wall, and say I am operating in the range of say few hundreds of nanometers. So in this scenario, what will be happening when I am in few hundreds of nanometers, then molecular effects will also come into picture. Okay, so I will not be having pure velocity of the surface purely at rest, because at this point continuum is not fully satisfied. Okay, so that's why we will be finding that velocity of fluid at this point is having some magnitude. But how to define velocity at this wall? So for that we use this particular equation, that velocity, tangential velocity at this point minus velocity of wall is nothing but equal to beta times del ut by del n, where beta is called as slip coefficient. What is beta? Beta is nothing but your slip coefficient, or majority of the time it is also called as Navier slip length, because beta indicates nothing but parameter of length. See, this side you have velocity, so to satisfy dimensional homogeneity, n is the normal direction. Okay, you have to use this to be nothing but dimensions of length. So this is called as Navier slip length, and typically beta is nothing but the length at which if you extend the slope of this line, it will be coming to rest into the wall. So from surface of the wall to into the wall at which your velocity is coming to rest, that is called as beta, which is nothing but Navier slip length. Okay, so whenever we will be solving the problems of multi-phase flow, we may find some situations that I have a very extremely thin film. Okay, I may have some drop which is traveling over the surface. So in these scenarios, ideally if say a drop is placed on the surface, ideally at macroscopic level there should be drop molecule should stick to the surface. But we see that, say if you have some window, in the window when small drops are forming because of the condensation on the window glass, then after some time they travel in downward direction because of the gravity force. Okay, so that will be appearing as a singularity. Okay, that cannot come ideally because of the no slip condition, but there is something which is allowing that to move relative to the surface. So that is where actually Navier slip length can be important. Okay. Moreover, whenever you have your full scale continuum is not applicable in certain areas where length scales are very small, there you will be finding between the wall and the surface there is some relative motion. Okay, so that relative motion, if you have to specify, then one has to actually define the value of Navier slip length, and then this relation can be used to define the tangential velocity at the wall surface for a particular fluid. Okay, so generally whenever we will be looking into the interface from macroscopic perspective, the tangential velocity of the interface will be equal to same for both the phases. But if say when we are looking into the microscopic perspective, then we may have to use Navier slip model to define the difference of velocity between the two phases along the interface. Is this one clear? All are clear with this idea? So right now the approach which I am using is nothing but a two fluid approach. So in two fluid approach, rest of the portions you will be solving as it is, but for interface you need to define kinematic and dynamic boundary conditions. So kinematic boundary conditions I have defined. Dynamic boundary conditions, if you recall from the previous discussion, do you recall what are the dynamic boundary conditions? Earlier also I have defined. When we considered that, say, if we have a contaminated bubble or non-contaminated bubble, then how we can define? Yes, one is we have to balance the normal forces, and second is we have to balance the tangential forces. Okay, so that is something then I will take up in the next class. Okay.